Okay, you now understand the concept of different load types, deads and lows, wind loads, live loads. You understand how we create, as engineers, theoretical mathematical models. So this stick here with a triangle and a circle, now you can see that is a beam with a point load and a pin and a roller support. You'll be able to see that a lot clearer after your tube class this week. You understand everything has to be in equilibrium or else it'll fall down. And we understand how to formulate our equilibrium equations and now how to calculate reactions. So what we're going to do now is we're going to look at trusses. Before we do that, let's just review quickly. We have three types of supports. Okay, a fixed, three types of mathematical theorized supports. A fixed with three potential reactions. Remember, a moment is a reaction. It doesn't have to just be a force. Our pin, our triangle, represents restraint in the x and y direction, and our roller represents restraint in just one direction. If this roller here, we could draw the roller as so, and in that case there, the restraint would be in the horizontal direction. So the restraint is at 90 degrees to the support, the flat support. Okay, so this is one I photographed when I took my son to his soccer a few years back. What type of support would you expect to see on the bottom of a flagpole? Fixed support. This was actually, you can see there's a huge lean on this. I've never seen a flagpole like this before. This was a very wobbly flagpole. They can be wobbly, but that's, instead of saying, let's have a rope on this and let the flag up and down, the way they get a flag up is to undo these two nuts here, okay, and tilt the whole flagpole over, put the flag on, put it up. Now, I don't know if there was just a bit of a dumb person working that day, or if this is such a tough area or a rough area you can't have a bit of rope hanging around because it would get trashed. But here I would say, well, this is a fixed support when it's in use, and to get the flag up, it's a pin support. You can see here, it allows it to swivel up and down. Okay, enough of my rambling on. So you know about your fixed and pin support types, but let's just have a look at what they support. So in this first case here, we have a simply supported beam. So there's a support at either end of the beam, a roller and a pin support. Sometimes our beam can run continuous over our support types. So at this point here, you would just have unknown vertical reactions. When, however, we come and look at what's happening within the beam, okay, within the beam here, there is still an internal moment there. Just remember that when we get to bending. People think, oh, it's a pin support, there's no moment there. There's no moment reaction there, but within the beam there is an internal moment. So we have our continuous supports, we have what we call our cantilevers, where one end is a fix, or you can get a cantilever similar restraint to a beam by having the beam run beyond one of the support types. So they're all our stick drawings. Here in reality, let's see what we can find in this bit of building here from Chatston that I illegally photographed, because you need a license permit to photograph anything there. Okay, so what we're looking at here is these members through here. They're all simply supported beams. You can see, I know it's very small in here, but you can see there's only 1, 2, 3, 4 bolts supporting the beam to these very deep universal beams. So there are simply supported beams. Then up on this top one, I don't know if you can see there's a thickening to the flange, top and bottom. So that would be where the actual beam itself is either bolted, as well as being bolted along the web, is bolted at the flange, or fully welded. I'm not sure if that's fully welded up there. So this member now, because it is rigidly joined, is effectively a continuous member through here. Then what else can we see? Well, here, if you just consider this end section here, you could say, well, that's like a cantilever beam because it's rigidly connected to the beam on the other side. Or down here, you have the situation where you have two supports. One's a pin, one's a roller. Don't really care which is it which. So here in reality, you have our stick drawings, theoretical stick drawings, just so they mean a little bit more to you. I wanted to show you that. Okay, here we have a case where we have a beam. This is just the final case that confuses people. And we have an internal pin here at C and a pin support at B. So this member here, okay, what we have is we have a continuous beam running past C. So if I was just modelling that horizontal member, I would actually model it as a pin support here and a roller. Or I'd have another pin. I'd have a support here in the X and Y direction here. So this member that's running at an angle, because it has a pin at either end, this type of member is a link. It can actually only transfer load that runs along the axis of the member. If you grab anything, I haven't got anything here to use. If you grab a member and just hold it at either end with pins, if I try and apply a load off centre, can you see it will rotate? So a member with a pin at either end can only carry a load along the axis of the actual member itself. So that's why when you come and analyse this member, if this angle in here is theta, and I call that V and H, then we know the relationship between V and H, because we know if I draw on here now, V and H running along there, one could say that V on H is equal to tan theta. So we can define a relationship between those two forces. Anyway, so just to go over again, a member with a pin at both ends and no lateral load applied can only experience axial tension or compression forces. This was in the exam paper one year, something similar, and everyone stuffed it up. Just remember that. Okay. Today is all about trusses. This week is all about trusses. We're moving on. We know how to calculate reactions. What is the next step? What structural form shall we look at? An arch, a truss, a beam, a cable? We're looking at trusses. So in this subject we're looking at trusses and beams. We're not concerning ourselves with arches or cables. They're not as common. So the first thing is we'll go over what a truss is. And then I will teach you the two methods we use to analyse for the internal members in the truss. Our members are carrying forces in them now, so we have to now know how big those forces are in order to design them. So what is a truss? Basically a truss is any structure made up of triangles. So in your bike, years and years ago, Project 1, hopefully you've downloaded it and had a look at it. I'll talk about it on Wednesday. If you haven't downloaded it and looked at it, please do so before Wednesday. Our first design used to be a bike design, where you would calculate the forces in the bike based on the weight of the person on the bike. So why triangles? Because triangular elements are stable. If you had a rectangular element with pins in the corner, you could see it would move in and out. So anything that's triangulated is stable. So trusses are everywhere around us, not so common in your average day-to-day structure, but here in the city, a lot of the footbridges now are trusses. The architects quite like to actually expose the structural form. It's quite trendy now to show a truss as a truss, to display that on the outside rather than hide it behind cladding. This is in Melbourne Central. You'll see a lot of triangulation in here as well. This is the Punt Road Bridge at Richmond. And even in our own building here, Building 60, you'll see some trusses in there where you see diagonal members. So have a look around and walk down the street and go, oh, there's a truss. Feel really good about yourself. Why not? It's the small things in life that make you happy. Okay. Trusses are actually efficient structural forms for long spans. We have something that needs to span 2 metres. The easiest thing is to get a beam, is a piece of wood. You don't want to go making up a triangulated piece of wood. Okay, it's expensive. So trusses cost more to manufacture, but they are very efficient when it comes to long spans. So here is just an excerpt from some book about steel bridge types. So you don't need to know what all these bridge types here are, but basically that first group of bridge trusses, the plate girder bridges, are beams. And you'll see here they're efficient from 0, 10 metres up to about 80 metres. Beyond that, we then have the trusses that fit within our next region. Then our arches can span further, though we don't have many arch bridges nowadays. And then finally cables. So the cable suspension bridges are the most efficient for long spans, but our trusses are in here. So this is why in buildings you don't often see trusses. However, in saying that, they are starting to pop their head up in domestic timber construction. Why? Well, because it's quite difficult to have big pieces of wood now. They have to laminate them together. Years and years ago, you'd cut a big tree down and get yourself a big piece of wood. Now that timber is more expensive, okay, it has become cost effective now to actually make up these trusses with aluminium diagonals and timbers top and bottom. So you have them here in the flooring as well. And this also allows services to pass freely through without having to drill a hole in your section. Okay, there are different types of trusses. These names all generally relate to the person that basically came up with them. So, but a truss is a truss. When it comes to the project, which I'll speak about on Wednesday, what type of truss should we put in? I don't know what they're all called. All I know is this one here. I mean, it has various names. The ones that are more common are our Warren truss, because of this W in here. So if you listen to the radio, you've heard of, I don't know what he's the minister of, but one of our politicians is Mr. Warren Truss, and I have a chuckle every time I hear his name, and I wonder if his dad was an engineer and decided to call him Warren because he knew that was a common truss. So our Warren truss is up here. That's because I'm pretty nerdy, so you don't have to think like that. It's called a modified Warren there, but generally I call it a Warren with vertical members in there. Fink and Howe were railway bridges. So trusses actually came into their own with the coming of railways. It was the coming of railways that developed trusses in England and in America, and that's because now rivers had to be passed. Okay, and these spans of rivers were too far for beams. In America, in England, they would build a nice old arch bridge out of stonework. In America, they wanted to move east quickly. So how do you make a quick structure to span a river? Out of timber. So a lot of these bridges in America, these truss bridges were built out of timber. So it's the railroads in America that actually helped develop the usage and the development of all these different truss designs. So Fink and Howe were 19th century engineers or builders of bridges. So there are K trusses. You can see a K in there. I'm not sure with camelback because of the shape of a camelback. So they all have wonderful original names. We're going to limit ourselves when we do the project to Warren, and we commonly call a flat truss like that has that shape. We call that a Howe or a Pratt, and the other way round, when it is that way round, we call it an N truss. You can see the letter N in there. So don't care what you call them. I don't even know what they're all called. They're all trusses. They're all triangulated. So we have a truss, and very originally we call the top horizontal member the top chord member. The bottom horizontal member, the bottom chord. Diagonals, oops, that's pointing to the wrong thing. This diagonal should be pointing here. And vertical posts. So when you come and do your truss design, you are going to look at the design of a typical top chord member, a typical bottom chord member, typical diagonal, and if you have verticals, vertical members as well. So this entire structure here is a truss. So what I don't want to see is I don't want people coming to me and saying, here is my truss. This is just a segment out of your truss. Your truss is the entire structure between supports. Okay? Okay. So let's go back through and how do trusses actually carry loads. So remember we have our 4 structural actions, axial compression or tension being one, bending which causes curving, shear distortion and torque twisting. Trusses transfer loads by members experiencing either tension or compression. So the truss as a whole does appear to curve or bend, but all these individual members here, they're actually either experiencing either tension or compression axial forces in them. So if you think about how a truss works, here's the very simplest type of truss, just 2 members connected up to a wall. Can you imagine here when we pull down with this force P, I don't think of tension compression forces. I ask myself what's stretching, what's squashing. So when you pull down with this force P, I think you can all imagine that this thing wants to move down. So you can see our green member is in tension, it's stretching. And our bottom member here, if that member was just a piece of string or a cable tie, that P force would swing in. So there must be a compression force in the horizontal member. So you can continue working your way out here and ask yourself, this P force pulls down, this member is stretching. If I take this member away, what will happen? This will move inwards, like so. So therefore this member is stopping it moving inwards, so it must be in compression. So you can work your way through and logically work out what member is in tension and what member is in compression. You do not have to do that. I will show you how to do the numbers, and the numbers will tell you. If you end up with a negative number, that's telling you it's in compression. So you don't have to actually be able to see this. However, it's useful if you do understand how trusses work. So you can see here this P force effectively is coming up this member, then it's going down this member, and then it's coming up this member, and it's been restrained up at the top support here. So the loads transfer through all the members. Okay, you can't say it's just going up that member and across. So the loads can't go from a vertical component of load to horizontal. So they need every member in the truss to work if it's a determinate structure. Now in saying truss members transfer loads by either being in tension or compression, we're actually making 2 mathematical assumptions. We are assuming the trusses are loaded and supported only at the joints, and I forgot to point out what a joint was, but I think it's fairly clear, obvious what a joint is. Where all these members are connected together, we refer to these as joints. So the first assumption, as I said, was trusses. We're assuming the trusses are loaded and supported only at joints, and our second assumption is all joints in a truss are pin joints. So let's have a look at the fact that all loading is applied at joints, whether that's a reasonable assumption. Well, it is actually a reasonable assumption because when you look up the structural form of a lot of truss members, you'll see what we have: our primary structure, which is our truss structure, and our secondary structure. When you think how you build this, you would put the primary structure up first, then you would come along and put these blue members in here. So they are your secondary structure. Now when we put this secondary structure in, we usually have it line up. So you'd have a joint in that connection in all 3 directions. And thus, when you consider loading on your decking in between the 2 trusses, if you consider a load path, if you consider a point load as shown here, that load transfers into this white member, then into these blue members, then into the truss member, and then into the supports. So the load path would be, well, hang on, I'll put a load here on this stringer. So here we have a load in the stringer there. How does the load get out? It causes the stringer to bend. Okay? Then the stringer itself is supported on these secondary floor members, which are also bending. The load gets transferred out here to our truss members, and then through truss action, the loads then reach the support points here. So thus the assumption that trusses are loaded at joints is usually acceptable, since the secondary structure is usually designed to line up with the truss joints. Now our second assumption, that joints are pinned. Now have a look at this railway bridge, Punt Road. That is not a pinned joint. No way could you call that a there is no way I could prove that was a pinned joint to you. It is not. However, if you do analyse this, computer analysis shows that if loaded at the joints, you do get moments and shear forces developed, but they are extremely small compared to these internal forces I'm talking about. Thus, the simplified assumption of pin joints everywhere is acceptable. And by making this simple assumption, I can teach you how to analyse a truss in 2 hours. Okay? So it allows the mathematics to be simplified dramatically. So do we believe there are no bending and shear if our joints are all rigid? No, there are minor bending and shear actions in our truss. However, they are minor compared to the actual axial forces in the member. Okay, so that's what a truss is. Now we need to look at the stability just to ensure our truss is stable, and again to ensure that it's determinate. So when we look at trusses, we look at external and internal stability. External stability just relates to the reactions. So as I showed you in the lecture last week, to have a stable structure, you need to have a pin and a roller. If you just have 2 rollers in the system, there is no horizontal restraint here. So that would be considered unstable in the horizontal direction. When we look at internal stability, that relates to the arrangement of members. So for our truss to be stable internally, it has to be fully triangulated. So here, in here, because we're assuming there are pins everywhere, as that is not fully triangulated, if I applied a load on here, this thing would move down, and then this side here would move up, and these things would stay the same length. That's a horrible drawing. We have a model that we'll show you in the practice class next week, a model made out of paper, that you can see that happen. So basically, external stability, check your supports, that you have enough of them. Internal stability, ensure it's fully triangulated. Easy. So before you get started, is your structure stable? Of course, next week in the problem set, the questions we ask you to do, they'll all be stable. There's no point asking you to do one that's not stable. Okay? If it's not stable, you have to stop. If it is, then the next question you have to ask yourself is my truss determinate? So just to remind you, what does determinate mean? It means, can the reactions and member forces be determined using equilibrium? We're working in 2D, 2 dimensions, so we have 3 equations of equilibrium. So externally determinate means, of course, the supports can just, if it's externally determinate, we've been through this last week, the supports provide just enough restraint. If it's externally indeterminate, we have more than enough supports. So here on the left-hand side, we have 3 unknown reactions, so we can calculate those reactions. That was the left-hand side. On the right-hand side here, we have 4 unknown reactions. We could not proceed. We'd say that was indeterminate, externally indeterminate. So we need our system to be externally determinate and also internally determinate. So what's the difference between an internal and determinacy and indeterminacy? If you have just enough members, if you have your members triangulated only once, this is an internally determinate system. If you have extra members here, now the way this is drawn, there is no joint in the middle here. What you have here is you just have 2 members going past each other. So can you see you have an extra member in here? And if you now try to calculate all the member forces in there, you would not be able to do it. There are extra members in there. Why do we put extra members in there? Well, we sometimes purposely build in indeterminacy. If you're building something in an area, a war zone, or near transportation, near traffic, on a bridge, where the removal of one member will cause the whole structure to fall down. That's a problem. So we would put extra members in there. So do you scratch your heads and look at everything? No, there's a formula I'll show you in a minute. But just to go over this indeterminacy, and indeterminate structures have more than one load path. That means the load is capable of getting to the supports two different ways. So if we remove one of these diagonals here, we can see the load happily will reach the supports. If we remove our other diagonal, our loads again will happily reach the supports. So thus we have more members in there than is what is minimally required. So there is a formula we give you to actually define, for you to calculate what is stable and what is determinate. This is a very old formula. It's useful for determinacy. It's not useful for stability. You have to be able to look at a structure and go, okay, yeah, there's enough supports on that, that's stable. I won't explain that any further. I'll let you go to the practice class next week where that will be borne out when you do the questions. So anyway, we look at a truss. Is it externally stable? That means, are the supports okay? If you have enough supports, yes. Then you ask yourself, is it internally stable? So this is asking yourself, is it fully triangulated? If it's not, you use it by using this formula here, m plus r is either less than, greater than, or equal to 2j. That will then tell you whether your system is internally stable, stable and indeterminate, or determinate. So what does m and r and j equal? M are the number of members, r the number of reactions, and j the number of joints. The best way, of course, is through an example here. So if we look at our top truss here, what is a member? A member is the length between two joints. So in this situation here, we have 3 members. How many joints we have? Well, I think you can all see we have 3 joints. And how many reactions do we have? Not how many supports do we have, how many reactions. Because we have a roller and a pin, we have 3 reactions. So looking at that system now, m plus r equals 2j. So thus this system here is determinate. And I should have said stable first because stable is the important thing. It'll stand up. And knowing it stands up, we can actually calculate the member forces. Down in this second case, m here, how many members do we have? 1, 2, 3, 4, 5. 5 members. How many joints do we have? 1, 2, 3, 4. 3 reactions. So again, m plus r this time is equal to 8. 2j is equal to 8. So m plus r is equal to 2j. So that is also stable and determinate. So you'll be using that formula next week in the class just to run through what's determinate, what's indeterminate. Okay, moving on. Let's calculate some member forces. That's what we want to do. And when I say moving on, just one more thing we need to look at. The problem set questions sometimes have a funny numbering on them. When we have a truss, generally nowadays, if you have a truss like this, you would designate each joint a name. And then you would call this member here member BC because it runs through between joint B and C. However, another way of naming members is by looking at the letters either side of where the member runs through. So this member here would be member AC and this member here AB. And back in the old days when we did member of joints and we didn't have calculators, we would actually use protractors and rulers and actually draw these as vectors. And we would actually see in this system here, you can see when you add your 3 member forces together, because they don't all come back to a point and form a closed triangle, you would see here we have a resultant force in here. So in this instance, there is no equilibrium in this system. Okay, so to calculate internal forces in trusses, we use equilibrium and free body diagrams again. Have I actually taught you anything in this subject? No, I've only taught you how to apply what you already know. You already know about equilibrium. Oh, well, I told you about free body diagrams. But what I want to get across to you is, what I'm about to explain to you now is the same method we use to calculate reactions. We're just using equilibrium and free body diagrams in a slightly different way. Before we do launch into trusses, I just want to consider what I call a subset of trusses, which are triangular cable structures. And in triangular cable structures, I think you can all imagine all these members here will all be in tension only. So think of these all as bits of ropes. So for these systems to work, the axial force in them must only be tension. This taxi comes from a problem in the problem set next week. Okay, so how do we calculate these forces? We use free body diagrams. Remember what a free body diagram is? When we isolate part of a structure, we call it a free body. Here we've taken the top floor of our building and we've looked at the connections and we've said one end is a roller and one end is a pin. Then we redraw our diagram with all the forces on it. So where we had our roller, we draw our one restraint. Where we had our pin, we draw our two restraints. And of course, this system now is stable, it's in equilibrium, so we can just use our three equilibrium equations to solve for our three unknown reactions. Well, when we want to calculate internal forces, okay, we do the same thing. If all stable structures are in equilibrium, all the internal forces in them are also in equilibrium. So to find the value of an internal force, the boundary of a free body diagram can cut through the member, exposing the internal force. We did that when we had our piece of paper in our second week class, and we pulled on that piece of paper. And to work out what the force was in the paper, I said, well, why don't we just cut through here? So our free body diagram here is now our external force and now the force in the paper. And by doing that, we calculated the force in the paper. Well, we do exactly the same thing here. We have our man hanging from these two cables. We say, okay, we're going to, for our free body diagram, cut through these two cables. So here is my free body. Here is now my free body diagram. The weight of the man, 80 kilos, 0.8 kilonewtons down. And where I've cut through now, you can see my letter designation, ABC. I have a force to the left now, force AB, and a force to the right, force BC. And this is a stable structure, so it is in equilibrium. So from equilibrium, all I do is I resolve all the forces in the x direction. So to do that, you just resolve these two diagonal forces into their x and y components. So in the x direction here, we have cos theta. Because this force here, BC, is pointing to the right, it's positive. And because FAB is pointing to the left, it's negative. And you then have two equations, two unknowns you solve, simultaneous equations, basic maths. So things to note here, when you draw these unknowns, always draw the arrows away from the joint. So an arrow drawn away from the joint indicates a tension force. You get a positive value, you know it's a tension force. You get a negative value, that's the maths telling you it is now a compression force in that member. Now, if you look closely at our joint here, all the forces here, can you see they all come to a point, that point being the joint itself. When that happens, we say all our forces are concurrent. But what that means is now, taking moments does not give us any more information. So, as such, because our forces are concurrent, There's no rotation in our system, and thus when we use this method, we can only solve for two unknowns because we only have our two translational equations that will give us information. Of course, the sum of the moments does still equal 0. We do have rotational equilibrium. However, if I took moments from the joint, I would get, well, 0 equals 0. If I took moments off in space and worked out the perpendicular distance of all my forces, I would still get 0 equals 0. So I get no further information. So when you use the joint method, you can only have two unknowns at a joint. So using that technique, we analyse trusses in exactly the same way, and we call it the method of joints. So, am I about to teach you a new method called the method of joints? No. I'm just going to show you how to apply equilibrium, free body diagrams, and equilibrium to calculate the forces in a member. So what is the method of joints? We use equilibrium to find the support reactions. We choose a joint where we only have two unknowns. We can only cope with two unknowns. We then draw a free body diagram of it and solve for the unknowns. And then you work your way through the truss one joint at a time, solving for the next force and the next force and the next force. Hence it's been called the method of joints. So let's look at this very simple truss here. The first thing we do is we calculate our reactions. So say now these reactions are now known. What we then do is we then find a joint where we only cut through two unknowns. So if I came up and started at this joint here, when I draw all the forces, the members in that circle, you can see here I have three unknowns. So I can't start at that joint. If I attempted to start at that joint, I would have 1, 2, 3, 4 unknowns. Sorry? What's up? Are we good? Okay. So I would have 4 unknowns here. But starting down at joint A, my reaction is a known force, and then I have 2 unknowns, and I solve for those 2 unknowns. So once we know the force in member FAB, we can then move across to joint B. And in joint B, we then have 2 unknowns because we know our force AB. And then from joint B, where would you move? To joint C or D? C. You'd move to C, and then from C, you'd move up to D. And if your loading is symmetrical, okay, you'd move to E, but you don't need to go any further if your loading is symmetrical. Which, in the problem sets we give you, usually the loading is symmetrical. In the bridges you're going to be designing, the footbridges, I'm going to allow you to make your structure symmetrical, make your loading is symmetrical, so you only need to analyse half the truss. Okay, so let's do some numbers here. We have a very, very simple truss here. You really can't get much simpler. You have 90 kilonewtons applied down at joint B. First thing you have to do always is calculate the reactions. Please don't get to the exam and get yourself confused because you don't know your reactions. Calculate your reactions. So here, we're just using equilibrium to calculate our reactions. Forces in the x direction equals 0. I just have my R3 force, so that equals 0. In the y direction, I have R1 and R2 minus 90 equals 0. And then I need to take moments. Taking moments here at A, well, I have my 90 kilonewtons here times that distance 1 metre. Because it's going clockwise, it's negative. And then I have my second force here, R2. This distance in here is now 3 metres. Does R3 cause a moment at A? No, R3 runs. If you trace that force as a vector, it runs through point A. It causes no moment. So we calculate our reactions, and now we choose a joint with only 2 unknowns. Remember, there can only be a maximum of 2 unknowns at a time because the forces at a joint are always concurrent. They always come back to a point. So let's start at joint A. In this particular problem, we could actually start at joint A, joint B, or joint C, because at each of those joints there are two unknowns. So looking at joint A, very importantly, what you do is redraw your joint. Please don't think I couldn't be stuffed doing it and then make a mistake along the way. In the exam, your calculations need to be legible. In real life, your calculations need to be legible. If someone can't read them, they'll throw them back at you and say, don't know what you've done here. Okay, so we draw our joint with our two unknowns using the numbering system AB for our diagonal member and AC for our horizontal. And this system is in equilibrium. So very simply, I've resolved it here just to show out a bit clearer what's going on. This diagonal member has a cos and a sine component. So now when we look at all the forces in the x direction, we have the cos component here, FAB cos 45, plus FAC, and that all equals 0. In the y direction, we have our 60 kilonewton reaction up. Then we have only the sine component here of our diagonal member. They equal 0. So from this second equation, we can solve for AB straight away. And once we know AB, we then come and we substitute into our first equation and solve for FAC. Now remember, always draw your arrows away. I drew this force towards. Is this force of 60 here a tension or a compression force? It's actually neither. It's a reaction. So the reaction, please draw the reaction in the direction it actually acts in. People draw it away and call it negative. No, it's not an internal member force. Draw it where it is, okay? And then draw your other forces away. Now here we got a negative value, so that means member AB is in compression. And if you look at the structure, you can imagine the 90 is pushing down. It's squashing AB and BC. AC in tension, well, if I remove AC, the whole thing wants to open up. So AC there would be in tension holding it all together. Okay, we know those two forces. Now we work our way through the truss one joint at a time, solving for the member forces. So let's look up here at this top joint. We could actually independently solve this, but now we know one of the member forces. So this is the procedure you go through. We know this force here is minus 84.9. That minus means it's a compression. Now, if you want, you can turn it round and call it 84.9. I, however, prefer to stick to the convention, always draw your internal forces away from the joint. But what that means is now, when we now take equilibrium, and this is very important, this is where people go wrong. In the x direction, because my force here is to the left, you can see, because this force here is to the left, when I stick it in the equation, I would call it a minus. So it's minus FAB cos 45, and then I have my FAB force, that's a plus cos 26.6, and all of that equals 0. When, however, now I put my value of FAB in there, that has a value of minus 84.9. So in effect, I've got two minuses, and two minuses make a positive. So as I said, if you wish, you can actually turn your arrow the other way and end up with a positive straight away. And if you want to use that method, you can. People somehow then seem to get confused. Lizzie, now that I've drawn it the other way, is it a negative or is it a positive? I get confused. So I personally always draw my internal forces away. And if they're a negative, I actually call them a negative value. But be careful when you look at equilibrium. This negative sign here is because of the arrow direction. And this second negative sign here is because it was a negative value. Now in the Y direction here, we have a minus 90, forces going down. We have our minus FAB, because our force is down again, minus FAC, and substituting in there, you get an FAB value of minus 84. So both those members are in compression. We then can move on to our third joint. Well, in this case here, we've solved for everything. So if you have time in the exam, when you're doing your project, check your solution. So we've drawn this joint here with the known forces, with the calculated forces, and we just check we have equilibrium here in the X and the Y direction. Okay, we've still got 3 minutes. Give it to me, let me have them. Okay, arrows. When you look at the solution, the direction of the arrows, well, they are not what I expect them to be. When I see arrows like that, I think that's pulling apart, that's tension. And that is because the arrows as drawn show the forces on the joints, not the forces in the members. So if I separate this out here, the forces in that joint A will look like that. So if I now draw the member in there, the force on the member is equal and opposite. Force on that member is equal and opposite. And can you see here? Now, this arrow indicates the member is in compression. So just remember, the arrows are indicating the forces on the joints, not the forces in the members. Or just remember, when you see the arrows, they're opposite to what you think they are, if you consider it to be the forces in the members. I did want to do one more thing, but I'll see you all on Wednesday.